Okay, hello everyone. We are going to do a working session talking about multi-computation and language design around multi-computation. And just some quick reminders about where we are with this. We've been looking at a variety. We're trying to add minimal features to the language to allow it to be multi-computational. We are trying to make sure that we hit various kinds of functionality like find replace path. We're trying to make sure that we can, I think there's a reasonable summary here of what we're trying to do. And we have been looking at, gosh, what is this? Okay, we also were looking at Nick's work on using hypergraphs as the raw material for everything as a way to make it clearer. I mean, hypergraphs as opposed to tree-based expressions that point to the symbol table, hypergraphs that kind of, in a sense, have atoms everywhere rather than just having tree-like expressions with the repository of atoms being in the symbol table. Does that make sense?
Yep.
And so it's kind of, this is a different approach and an interesting approach to kind of generalizing the idea of expressions and generalizing the idea of the symbol table. And I think this is something we want to look at some more. But through a partial misunderstanding, we have some specific topics that we want to cover to begin with here today. And let's get started with those. So the first one is about type theory. Oh, I see. Okay, I remember what this was now. I'm now a little less clueless here. Okay, I remember what this is. Yes. Okay, yes, I did want to look at this. Okay. I'm trying to, okay, so first thing is a review of type theory, homotopy type theory, etc. This was a note from Michael about types and patterns and the relationship between types and patterns. Who wants to launch here and talk about this? James, are you ready to talk about this?
I am ready, but perhaps since Michael kind of initiated or piqued our interest in this, perhaps he has some opening remarks to make about this.
After we talked the last time about it, I thought afterwards that this identification of types with pattern and terms with pattern instances has a couple problems. The biggest one being that if you have a term in classical type theory, there's a unique type. If you have a pattern instance, you can't derive a unique pattern.
Fair point. Is there a unique type? I mean, isn't there a hierarchy of types?
There's a hierarchy of types, but every term has a type.
Okay, so wait a minute. If I've got an integer mod 2, no, an integer of a certain size, is that not a subtype of the general type of integers or numbers or whatever else?
Oh, subtyping is a whole own can of worms that we probably don't want to go into.
But the argument that you're making is that the difference between types and patterns, okay, so your claim is that, okay, so this is about type theory versus patterns. And let's save this away in an appropriate place. Okay, so your claim is that every expression has a type, has a unique type.
Every term. Because it doesn't think like expression in type theory. There's not even the definition of such object.
Okay, has a unique type. But every expression does not have a unique pattern.
Exactly. That was my main
Okay.
No, gee, I feel like it has problems.
Okay, so can somebody comment on this? I mean, this is clearly true, right? You know, if I have, we got a bunch of background noise. Could somebody kind of arrange themselves better?
So maybe one, okay, go ahead.
Thank you. So as far as I understand, one can develop, for example, all of lambda calculus and the calculus of constructions with terms having unique types. One could add subtyping, but it's a complication that in principle is not needed. And I think something similar could happen with expressions and patterns. We could consider a situation in which every expression belongs only to one pattern. It's just that it's not our case.
Why is this a requirement?
Say it again.
Why is it a requirement? Why is it needed that it's a unique pattern?
But otherwise, unique pattern, I'm not arguing in any form, but that every term has a type is one of the fundamental assumptions in the whole game.
How is it used?
Yeah.
The fact that every term has a type is surely true. The fact that every term has a unique type is less clearly used to me.
Oh, I think it's a lot used for uniqueness theorems and decidability. Otherwise, you would have a tree to follow and such things.
I think it's a simplification. It's a major simplification, and if you can live with it, you should live with it.
So for reference, I think that I'm not totally sure how this relates to like the way the compiler does types, but in the compiler, I mean, so first of all, in the compiler, there are like subtypes and so on, and there are abstract types and then concrete types. And every object has a unique concrete type, but they might be members of several abstract types. And similarly, there's a thing called for all type, which is sort of like is very similar to patterns. And one of the things that I think we've talked about a bit is trying to basically replace things like for all type with patterns at some point in the future. But there's some issues with it. But
can you remind us how for all type works?
The syntax is basically the same as for all. So you'd say something like for all type of T, comma, and then you'd make up some type in the second argument. So, you could do a function type like, do list brackets, T arrow T. That would be some function that takes any T and returns the same type back. List around only the left side of the rule. But you could imagine writing something like that as maybe, T underscore arrow T underscore or something like that. The issue is the reason why we haven't done this in the compiler is both because it means you have to parse these patterns and it's not necessarily clear what pattern constructs are supported and what aren't. But the other reason is there's some issues like conditions. So for all type has a second argument, which is like the conditions that you would apply. So like, for example, T has to be an element of the integer's abstract type. And it's not as clear how to do that with patterns. That's not really confusing, but yeah.
Okay, so hold on. Let's try to understand. Okay, can we see what consequences it has to, the Curry-Howard correspondence, homotopy type theory, all these kinds of consequences. Can we talk through how those work and how they relate to the idea of types as patterns? Right, because the real question here is how equivalent or not is type theory to pattern, to dealing with patterns? The correspondence, one hypothesis about, look, what is the WL analog of type theory when it isn't type theory? If that makes sense. Right? If we don't have types like in the compiler, what is our closest analogy? One obvious analogy from ages ago is, heads as types. That's one possibility. Another one might be patterns as types. Can we get some idea and analysis of what's going on here? Are those equivalent, those ideas? Or is it the case that patterns as types says, for example, let's say blank integer, comma, blank integer. That's a type. Whereas this is a more explicitly stated type where there's an explicit head lying around that tags the type. Comments here?
All right. Yeah. I also have this exploration, old one. I dig up an old notebook that explores this idea.
Can you?
And so it is also in the same agenda. So it's like I have these notebooks there.
It's a little bit a sneaky point is that underbar integer is matched by integers and integer of chunk.
I understand that.
Okay. Yeah. It's a pitfall, a potential.
Right. There are always pitfalls. What is all this background noise? Somebody is like anyway, never mind. Okay. All right. Should we look at this here?
Maybe the second one. Just scroll through it. It's just you will see some.
This thing here, equational theory and inference, or what? Or
I don't know. It's an old notebook. I don't even remember much out of it. It's just an example of a bunch of patterns that you can do with some relations to the type theory, especially the second one, the second notebook.
Which second notebook? You mean this one here about
the second section?
Equational theory and inference.
The one is it says proof calculus.
Oh, this one here. Okay.
Yeah. It's like there's like some code for constructing explicit terms and work with those terms.
Matter variables. Okay, where do we start here?
Maybe where it says begin.
Huh. Okay.
I think it's a good. It's like I think my idea was a simple idea. It's like you have a global thing with the valid patterns and also rules, right? And then you can construct terms that can match those patterns. So whenever a term that matches a valid pattern, it's a constructible term. Otherwise, it always returns a failure. And then you like add a pattern. Then if you make a term that matches it, it's a good term. And then you can prove stuff with it by just composing terms together.
How do you differentiate between there is no term and you can't find a term?
Well, you always have to construct a term. So you always define a type first when you want to construct a term of this type.
But kind of like the term is a proof. So I could construct the type, the Riemann hypothesis is true, but to current knowledge, we will not find a term.
Yeah, you can't make an actual expression that matches this type that you've constructed.
I mean, in constructivism,
no, there's a difference between you can't in principle or you're not be able to because of limited knowledge.
What's the difference though under constructivism? If you can't produce a proof, then by default, you presume the proposition to be false.
No, absolutely not. This is not how Lean and other ones work.
Well, how could that not be the case? If you can't prove it constructively, why would you presume it to be true?
But it can't.
Because it can be independent from the rest.
No, but hold on. There's two different points here. One is there a bound on how long the proof needs to be? I mean, there are many things that are provable, but the proof is extremely long. And yet there are other things which are independent.
Wait, but hold on. Is this something where in order to make one of these term objects, you need to basically provide it with an instance? And so it's another,
yes,
you are doing all the work here. So if you wanted to, right. So this is not doing any proving or anything like that.
No.
Right. So let's just understand. Let's give an example of a non-trivial sort of theorem stated as a pattern where its proof is an instance of the pattern. That's what we're talking about here, correct?
Right. Yes. I think you'll find some of the examples there.
theorem is a pattern. Its proof is an instance.
There
Okay.
exists a Fibonacci number that is prime.
Okay, what's that as a pattern?
Maybe you could also do square root of 2 is rational. That's an easy one.
Okay, so what is the pattern in that case?
Well, first you have to define natural number, a square root, and what is rational. You know, it's
Rational,
actually,
you could just do matches, n underscore integer, y underscore integer, or something like
Yeah,
that.
right. X underscore integer / y underscore integer equals square root of 2. Is that right? Is that our theorem?
Well, I guess.
No, it does not exist the left-hand side such that.
Right.
Okay, so
Maybe
then,
makes it a bit harder.
okay, can we do
I
that
would
with-
say not of element.
No, you can't use element. Can't use element. This is pure pattern matching.
But any expression is a pattern. What do you? How do
Well,
you
I mean-
differentiate between allowed and non-allowed patterns?
yeah, except.
Right. So we're saying that, what are we saying? We're saying, I don't know
Maybe
how-
this is actually not the.
What's that?
Solution.
Christopher, you broke up.
I was saying that maybe this is not the best example because we're actually saying there's no solution to this.
Right. Well, so what would be a better example?
But then just revert it and say square root of 2 is irrational.
How? How do we say that?
Well, you have to have a pattern for irrational numbers.
Yeah, we don't have a pattern for irrational numbers.
Well, we can construct one. It's just some work required to do that. It's like, for example, if you have a natural number, you can construct a pattern for integers by just having something like minus, right?
Okay. I'm looking for, I thought I had a version of the irrationality of square root of 2. Okay, here we go. I have a few things here. This is square root of 2 is irrational in Peano arithmetic. Is this useful to us?
Maybe we should do something that's both simpler and has a solution, if you know what I mean. Like, I mean, even just something like, prove that 9 has a divisor that isn't 1 or 9. Or
Okay.
like prove that a number is composite or something.
Okay, fine. So let's say, well, okay, so I mean, that will be a very straightforward thing. If we say x blank integer times x blank integer equals 9.
Just
That's
1 plus
saying
1
9
equals
is a perfect square.
Yeah. So now what is the proof? The proof is we have a binding for x that is 3. Or prove that 12 is
minus
constant.
3.
Fine. But that's okay. We just, but why is this a proof? I mean, this is a proof by construction.
Exactly. Like if you would have an 8, it would still work as a proof. Because we would not be allowed to be let equal the one that decides. That would be outside of the game of patterns.
Okay, well then, so how do we make this work?
You can look at my example of 1 plus 1 equals 2. It's like you have to have
Where
a
is
definition of plus first.
Where is that?
I think it's somewhere there. I don't remember. It's in one of those sections, maybe in the last one for natural numbers. I think there's a section with proofs, and it should be called proofs. Yeah.
Oh my. What on earth is our objective here? Because by the time we've atomized things to this level, we're no longer using any of the serious apparatus of pattern matching.
What is the goal here really to be super pattern matching oriented, or is the goal just to do something like lean or cock or whatever?
Which does what at this level?
I mean, basically where you just write a bunch of these, terms, and then it tells you whether it's correct. And maybe it helps you a little bit along the way about, oh, you need to write something that proves this.
Yeah. What at Jonathan? I don't know if Jonathan is here. I think not, probably. Jonathan had produced some kind of toy proof assistant system like a year ago. Does anybody know what that does?
I think it was mimicking Ling very closely.
I agree. It was just a Wolfram language version of what Lean would do.
And what was that? What is that?
Start with a type and then with some help, step by step, build in a convenient way a term.
Okay.
In my opinion, I think we might be able to find a subset of our patterns that represents a part of the language that is needed in logic. But we are missing the fundamental type, which is the function type. We don't have a pattern that is the pattern for functions. And even more, pattern for the dependent functions, which is this for all type that we were discussing before. Perhaps having that, I mean, the arrow type, the function type, is a type that eventually will be implication under Carry Howard. And so it's a fundamental object in all of these. And I don't think we have a type, a pattern that is the pattern for functions eating arguments of this type and returning arguments of that type or values of that type. And that's the, yeah.
Well, why can't it be just rule? It's what you do with this function that matters. It's like even in other languages, the rule by itself is not doing anything until you run it for some evaluation. Similar with the rule, just like it's just a rule by itself until you run it with using some replace.
Well, a rule is a possible representation, right? So we're thinking of rules because this is typically represented with an arrow. Type, arrow, type. That's the type of a function that always eats arguments of a single type and always returns values of a single type. And then there is the for all type, the pi type, which is the unique type of a function whose values have different types depending on the argument they ate.
All right, so look, for us, the type of thing, so we've got a function, okay? And one thing we could imagine is a match for that says that, the match is, it's always an x blank goes to, or let's say x blank integer goes to, f of x of x.
But lots of functions are not written with function. And also, I think the fundamental problem is that there's nothing structurally about, like, there are lots of different things you can use as a head, which will evaluate. Symbols, functions, etc. And there's nothing structural about those things, except in certain cases, like if it's a pure function, where you can look at it and know whether it's going to evaluate or what it's going to evaluate to, without also knowing the state of the evaluator and down values and stuff like that.
Yes. Look, this type thing is a completely different model of how to think about computation than the one that we're using. And so the purpose of this discussion is to see, is there something we learn from this other model of computation that will be useful to us? And possibly the answer is no. It's such a different way of, there are plenty of, to give an allegorical example, in 1910, Whitehead and Russell had this model of mathematics that was the Principia Mathematica model. Mm-hmm. That model turned out to be not terribly useful in practice. Even to today, 110 years later, it's still, that model isn't the one most people are using.
Well, it depends on what you want to, depends on what application you have in mind. You see, I think just to recall the general topic of multi-computation, for instance, I think that type theory is really not terribly useful for multi-computation or computation or anything that involves the releological study of behavior. For instance, I think that it's basically not
Can you
helpful.
explain why?
Yes, I can explain why. So look, as I understand it, so let's say you have some proposition. You have some proposition, and then you're going to produce a term that constructs an object that proves that given proposition, right? Now, let's say that that proposition is proved by some sort of reducible computation. Okay, we can even take the example of constructing the integers. If I have a type, which is the integers, and then I take some program like 0, and then the successor of 0, and the successor of that, et cetera, I can just show you that algorithm. And you can understand that it constructs the naturals because it's an entirely reducible algorithm, right? Now let's consider that we have some proposition that says something about the behavior of a given program, which I think in principle you could do. So let's say you have a proposition that says that this program yields periodic behavior. If the proposition is some periodicity proposition, I can also give you a program that reducibly will give a constructive instance of that behavior. And you can know in advance, like let's say it's, periodicity 3 or something, has a period 3. I give you some program, that program constructs an instance of that particular description. Now, on the other hand, let's think about something like Rule 30. What proposition could Rule 30 feasibly serve as a constructor of? Or what kind of proposition could Rule 30 really prove? I mean, on the one hand, you could say something like, well, Rule 30 is a class 3 CA, for instance. But I'm not sure that that's really a specific proposition. You see, if you wanted to actually say something about the behavior of Rule 30, that Rule 30 gives a constructive proof of, really, because of irreducibility, that proposition is going to be computationally as long, the description length is going to be as long as the actual computation itself. There's no shorter description of that computation.
Let's try to summarize what you're saying. I think it's interesting. I mean, what you're basically saying is type theory is a way of sort of extracting a simple narrative. To describe something in terms of a type is to give some simple narrative about about some property of the thing.
Yeah, exactly. Right.
And many things that we care about do not have simple narratives about them.
That's the point. And in the homotopy case, so, just to
Sorry, I have a question to this.
Okay.
I mean, the current idea is that type theory, at least at the level of lean or hot, can describe all of modern mathematics. And
Yes.
saying that's not really of interest seems a strange statement.
But mathematics, you must remember, if you take the view of releology or the overall computational universe, mathematics is this reducible, suburb within the computational universe. It's some pocket of reducibility. And type theory is basically a kind of address book for that reducible suburb within the computational universe. Now, in homotopy type theory, the whole point here is that the types themselves are spaces. You have different terms of that type. You have different, per Curry-Howard correspondence, you'll have different algorithms that serve as constructive proofs of that type. Now, the point here is that in the homotopy case, if you can also prove that these different respective terms prove the same type, then within this overall type space, there are going to be homotopies, there are going to be paths, higher paths between these terms. However, in the case of any computation that's irreducible, because the actual description of whatever kind of property is constructed by that given program, because it's going to be the exact same as the actual behavior of the program itself, whatever that space is for the actual type, for the proposition, that space is going to be exactly the same as the actual term itself, which means that the overall space is going to be contractible just to the single point, right? Because every program in homotopy type theory, every individual program is just a zero space, which means every single space is going to be contractible to that zero space, and you're not going to get any higher homotopy. So the point here is that all of these nice higher homotopies that you get in homotopy type theory, they depend on reducibility. If you don't have reducibility, if you have irreducibility, every program is basically unto itself, and you're not going to find any kind of translations between them, I claim.
Well, ultimately, there are translations from, computational universality. Ultimately, you can write an interpreter from one to the other. But I think that is at a level different from the level that homotopy type theory is considering. I think that is the same statement as the statement that Peano arithmetic can imitate set theory, which to mathematicians is like, that's nonsense. But as soon as you atomize, Peano arithmetic is perfectly capable of fielding a universal computer. And if you atomize things to that level, that universal computer can emulate set theory, but it cannot do it. It has to do it by emulating the separate bricks of set theory separately. It cannot semantically, generate set theory, if that made any sense.
Yes. Yes, I'm trying to think about, in the homotopy case, how you would model the universal computation. The universal computation, it seems like it's a computation that could inhabit any type. It could inhabit any space, which means if you have universal computers, it seems like any type, even a type that is just a proposition that describes the behavior of a program, those should all be inhabited by the program that yields them, and maybe also the universal program that can also emulate it. Something like that.
Yeah.
There are kind of trivial types that are not inhabited. And humans have no problems constructing them.
What's an example, Michael?
1 + 1 = 3.
Yes, but you see, the point is, Michael, that whole thing, like the statement that Peano arithmetic can't emulate set theory, as soon as you have the ones and threes and things meaning what you think they mean, then yes, all bets are off. But if you just are saying, as a matter of, we've got this thing called 3, we don't know what it is, can 1 + 1 = 3? The answer is sure. If we don't know what 3 is, if 3 is just some symbolic thing, we can choose to say that 1 + 1 = 3.
Yeah, basically, you could construct a proof that 1 + 1 = 3, but that will damage or rot your overall apparatus, so that you're going to get junk. You're going to get principle of explosion type behavior.
But you could make it much, much easier. You could easily write down some wrong identity that just uses implies the basic structure that we have. So it's easy to build a type that has no inhabitant. Because you said, my only point was that you were saying that every type is trivially inhabited. I disagree with this. The majority of type is not inhabited.
Oh, I don't think that every type is trivially inhabited. No way. No.
But the majority of type is not even inhabited.
That's true. Most types are empty.
That is my point. Yes.
Yeah.
You had said earlier that
most types are empty.
Okay, but so by a type, what we mean sort of more computationally is this is a template into which we fit some. I mean, there's some computational process that is supposed to be fitting into some template. And the claim is that if the thing you're fitting is computationally irreducible, it's tough to have a very interesting template.
Yeah. The only really accurate thing you can propose is just a description of the program, and that's going to be the exact same as the program itself under irreducibility.
Yeah. Okay, but so let's just look at this. So what you're saying is a type in these terms is a property. A property is associated with reducibility, because as soon as there's a property, you can say, then you can say something about something without having to just give all the pieces of the thing.
Yeah, Nick put it well when I was discussing it with him yesterday, which is basically the type itself is finite. I mean, if you take the naturals, for instance, naturals is a good example of this. You can state what the naturals are very simply. It's just a symbol, even though the program is basically an infinite program to construct the naturals.
Well, but you can't. I mean, plenty of things can be just written as a symbol. I mean, the halting problem, the solution to the halting problem for an infinite collection of Turing machines could just be a symbol, a function omega that answers it, let's say. So the fact you can package it is not really the point.
So let's take Fermat theory. It's in some sense non-constructive. We know that doesn't exist a solution to this equation. So how would this be represented as a constructive program?
I don't know. How does that work in type theory? The statement that something doesn't exist. How does that?
Equality. You just have an equality type and inequality, and you just make an instance of this one of inequality type.
You build a contradiction to some statements that you have, and there is no term.
Okay.
Yeah,
fine.
I mean, or you can build a function type from that type to an empty type. That's another way to express falsity.
I'm just asking, like, how a constructive computational representation of this could potentially look like.
Well, what Nick said about the contradiction, that's how you usually do it.
See, I have a feeling that the thing that's going wrong with types here is the exact same thing that goes wrong with types. Okay, so symbolic expressions have great diversity. You can make almost anything with them. In a sense, types are a more impoverished form of description of things. Whereas symbolic expression can just have this complicated tree structure that goes anywhere, a type, well, I'm not sure that's really right. I mean, it somehow...
No, this is definitely true. The set of rules that allow you to build a type is quite limited.
Yeah. But then the point is, the things you can build as symbolic expressions are, I mean, okay, one of the questions that was an underlying issue that I think maybe Nick was looking at is, if we take the point of view that we're dealing with patterns, and the patterns are an albeit impoverished representation of types, what operations do we want to be able to do on patterns, like unification as an example? Like, when are two patterns equivalent would be a good question to be able to answer, which we currently don't have any. We have no function that answers that question.
Random match would be the most natural one.
What do you mean?
I have a most general unifier.
I give you a pattern and you give me an expression that matches it.
I see. So, okay, so let's just make a list of functions operating on patterns. Okay, so an obvious one is pattern equivalent Q, which we may have. Maybe Nick has that. Another is random pattern instance.
And when in this game you allow condition or you don't allow condition?
Well, I mean, clearly allowing condition makes this unbelievably much more complicated. So
that's why I'm asking.
Let's start off with the not allowing condition.
Okay.
Okay. What are other? Okay.
What does random pattern instance? Is it a uniform distribution? Because
what the heck does that mean?
No,
I mean,
just
does it have
want
the same
one
probability of producing every member of the pattern? And then also, what does random pattern instance of underscore integer return?
One.
Always
17.
One? Always one.
No, I think it always return. I think it could return 17. I mean, look, Michael, this is exactly like your random instance of a geometric scene, isn't it? What do you return when you ask for random instance of a geometric scene?
I think it's different. The difference is, if I ask for a random instance of a geometric scene, I really want to see a scene. Here, I want to know, does there exist even something?
Going to be find pattern instance then? I just feel like random makes it sound like, I'm going to randomly sample.
Find is totally fine. Yeah.
Yes. Yeah. That's a better name. Find pattern instance. Okay. So that's no guarantee about what kind of a pattern instance it generates, just like find instance does the same thing. Right. Okay. Pattern contains what is it? But pattern, what is the right term? It's one pattern is a subset, sub-pattern queue or something. Is that the right term? I mean, is that Nick, do you already have some functions for this kind of thing?
No, not really.
Okay, but I mean, in these seem useful to me. I mean, we've had a function for sub-pattern queue forever because it's the way that we order, you know, f of 1 versus f of x blank and so on. Sub-pattern is different from pattern. I mean, like for example, well, is it the same thing as just asking, does one pattern match another pattern? No, it isn't the same thing because of pattern equivalent queue. Making sense?
Kind of.
Right.
Yeah.
I mean, look, if we have the pattern, this pattern here, okay, and then we have the pattern. Okay, you've already got this most general unifier thing, so you should be able to say for those two patterns. That's the question: is what given two patterns, right? It's a, you know, you want some kind of pattern. Find pattern unification. Is that right?
Yeah.
Okay.
But there's also, well, yeah, okay, yeah.
Another thing we do not have is, which we've been talking about several times, is find pattern bindings or find pattern rules or just okay, so what is that? That is if you say
It's almost replace.
Yeah, that's right. It's this, it's find pattern rules of this, comma, f of 3, 3, returns x goes to 3.
Yeah. People really want this one.
Right. What's the...
What about accept? I think this is, I mean, I guess maybe any of these issues are kind of solved with replace. So maybe it's just whatever replace does. But there can be cases like with accept where you can bind an x to something that's like, you know, anything that's not an integer, if you get what I mean.
Yes, I understand. So I mean, the question is, what does it do? Okay, so find pattern rules for, what is the right term? Except, well, you say x colon.
No, I think you can say accept of x underscore integer or something like that, or it's with the second argument of accept.
Wait a minute. So if I say something like this, is that what you're saying? Look, there are cases in which the thing has dwindled and there is no binding. There are cases like that. And I think what we've done, you know, that was a long-standing bug, you know, a multi-decade bug. And what we did there was eventually just say it's not going to match in that case. If we can't find a binding, it doesn't match. You know, a subterranean.
Well, I know there's a bug. I can maybe find it. I saw just like, I don't know, 6 months ago, which was with accept, where there are cases where basically you can get it. There are cases where it does match, but you know, for example, if you wrote this expression, you write replace of, you know, on the left-hand side of the rule, you have this accept statement with an X in it. And then on the right-hand side, you ask for X and it just doesn't replace X. It just binds X to itself. Because there's basically no.
What are you saying? What is the?
I might have to look up the bug to see what exactly the expression is, but I think it's using the second argument of accept. And so basically you can get.
I think I come up with this example. I don't remember it either. I think You just have to play around with it.
Yeah,
It was just a single line argument.
Okay, fine. Well, there's a way of getting a version of accept that works where you have an X that is theoretically bound to, any expression that's not an integer or something like that.
Yeah.
Okay. Well, so then the question is, in the case of find pattern rules, what does it do in that case? Because it could have two behaviors. One is a finds instance type behavior, or just finds something. And the other is where a reduce like behavior where it tries to represent the set.
Well, or it could just, or it could realistically, it could also just do what replace does, which is just to give some kind of fake answer. I mean, where it just returns X as a symbol or something like that. I'm not sure. Yeah, go ahead.
I was just going to say, I have this mode in the multi-replace function that if you just drop the right-hand side of your rule, then it acts like this multi-match thing, which is exactly what produce all the matches, possible matches to your patterns. So it's kind of the same thing.
Okay, can we see that? Is multi-replace a WFR yet?
It is. It's just this version is not. So you have to find it in the function repository sources.
In the physics project function repository sources, or somewhere else?
Yeah, code development function repository sources, revisions, and there's a multi-replace version that has this behavior that acts on rules without right-hand side.
Should I just run this?
Yeah.
Okay. Now what do I do?
I'll try this example with.
Which example?
With fxx, f33, for example.
So which way around is it? Like that?
Expression, then I think the other way around. Though if you change the method to by substitution, it doesn't matter.
Do I update now this thing? Yeah.
Yeah.
That's pretty cool, that nice new blue thing. Okay, what does that mean?
It's weird.
Is it wrong?
Maybe, or maybe not. It's like partially. And maybe you have to provide some option, like return matches goes to true. Oh, it's the same thing. Or pattern substitutions.
Okay.
Try
Well,
pattern substitutions goes to true. Then it should include what the binding to X happened. Like X, yeah. So like first there's a position. It says that the matching happened at the root position of expression.
Mhm.
X was bounded to 3. And then it's just the list of replacements, but the replacement is empty. So
okay, look, we've been through this before, but there are clearly multiple things that are useful here. Go ahead.
I have one more suggestion for a function that actually would be really useful for Oleg-style computation. I give you two sets of expressions, and I want a pattern that matches everybody in set 1 and nobody in set 2.
I see.
I give you x squared Bessel j of 5 comma x squared and such things, you know.
Right. So this is basically find minimal pattern. So this is asking that the simplest case of this would be given a list of expressions. Well, find sort of best fitting pattern. Okay, so find fitting pattern would be, if I give the expressions, like let's say 1, 1, 2, 2, UU, what I would like there to get is x blank, comma, x blank. And whereas if I say this, I mean, this is very reminiscent of programming by example. I want this and this, right, Michael?
Yeah.
That is a nice function. I mean, in a sense, we've tried to do that before in our programming by example types of things, but we've been more ambitious in what we expect there. But look, the thing we've discussed before, and maybe somebody can remind me what we came up with, is this it's not so much find pattern rules, but this is the replace. What the heck should it be called? It's kind of like detailed replace. Have we had this, or detailed? It's not even the replace. I mean, it's okay. If you were doing a replacement, where does it happen? Does that make sense? I mean, or where can it happen? Okay, I think this is what Nick's thing is specifically doing. I mean, multi-replace is finding those places where the pattern can be applied, correct?
Yeah.
So for example, if I go multi-replace here, and I say G of f of 3, 3, comma, H of f of 7, 7, right, I get that. Okay, I mean, I'm not sure that that's the right default, but that's showing me where are the matches and what are the bindings for the matches, right?
Right.
So, I mean, we definitely need a function that just does this. Where are the matches and what are the bindings? Now, what you're doing here is you're giving the minimal pattern rule to be applied at that. No, that's not what's going on. What is that?
It's not a pattern rule, it's just what patterns are getting binded with. Just replace all. It's like what you would replace the patterns with what expressions to make this expression to match.
Okay, but let's remind ourselves again how this all fits together. This whole question about where can the pattern be matched relates then to the evaluator, because the evaluator is looking at all possible matches and then picking one of them, whereas the multi-evaluator is picking all of them. And its criteria for which one to pick are, the standard evaluator is locally picking the first one that works. The multi-evaluator should be picking ones that satisfy some overall criterion. Is that right, guys?
Yeah, right.
Now, one question for Nick. How would we understand this function or other similar functionality, in terms of type theory? Is it consistent with type theory? Do we have to slightly modify the notion of type theory for anything multi like this? How do you understand it?
Well, first of all, our replacements are a bit more general than lambda expressions because they involve positions.
Mm-hmm.
So it's like positional lambdas that we have here.
That's interesting.
But other than that, it's pretty close. If you treat patterns as types and your lambda expressions are positional, then that's what we have.
Okay, so the issue here is patterns versus lambdas, etc. And the point here is to say that a lambda, aka function, just eats what it's fed. But replace.
Not quite. In the vast majority, at least in better type theories, you specify the type. So if you give it the wrong type, it will not eat it.
I know, but our lambdas are omnivorous.
Good. Yeah.
But the compiler's lambdas presumably are not omnivorous because they're functions that have particular type signatures.
And even rules, it's like when I say lambdas, I mean rules because they have a pattern on the left-hand side, which acts as a type. So it only eats a particular term of this type when the matching can happen.
Okay, so I see. So you're saying that replace, replace is like a typed lambda.
Yeah. And replace at is like this positional lambda.
Right. Replace at is the minimal positional lambda. But then already replace all. By the way, I am seeing some delay in typing, and I have a very bad feeling it's to do with the toolbar, and that should be reported.
Yeah, I'll make a note of that and report it.
Okay, replace all is like the multi-positional lambda. Is that right? So it's a...
Maybe it's a composition of positional lambdas, just because you can compose them as you compose usual functions.
Well, but it's a different thing. I mean, multi-positional lambda plus, yes, plus composition, because it can do more than one rule. It can apply unoverlapping, non-overlapping rules together. See what I'm saying?
So there are two different kinds of compositions that you can do, like sequential and parallel.
No, but it can't do the sequential. Sequential would be replace repeated. There's definitely a delay here. There's something wrong. This needs to be debugged. Replace repeated is like the evaluator and has, what we've discussed many times here, has, repeated sequential evaluation as opposed to multi-type stuff, or as opposed to, there's this positional multi that, the elements of a list can be operated on separately. And there's sort of non-positional, there's proper branchial multi where, what is the analogy between, okay, this is like talking about spatial hypergraph versus branchial space. There's the things that you can do in parallel because they are at different spatial positions. And there are things you can do in parallel branchially, so to speak. And, in our language, we have had the spatially parallel stuff, but not the branchially parallel stuff in the past.
Yep.
And the whole point here is to add in, to have a multi-evaluator. Okay, so the big picture is we are trying to make a multi-evaluator where, for the ordinary, we've said this many times here, ordinary evaluator, its workflow is, input goes to output via single way replacements plus fixed point. That's its scheme. So the multi-evaluator, as we've said many, many times, has to have different criteria for what answer it gives. Am I making sense?
Yes.
Okay, so the multi-evaluator has, as we've said many times here, I mean, we want something like multi-evaluate, and then, it has a criterion. We've talked about this. Nick, I don't know, have you implemented some of this now?
No. What I called multi-evaluate is just a multi-replace, but that acted on down values and up values because it evaluated those rules.
Okay, fine. But okay, look, you can get something that we don't have in the case of the ordinary evaluator, but the full manifest of everything it did, which is what you're trying to do here, right? We've not generally done that for the ordinary evaluator. That's what our evaluation graph stuff is about. That's what this type of representation is about, showing what the evaluator did in more detail, which is clearly useful. But what we want to do, and we've talked about this many times, is given conceptually that we've generated this giant multi-way graph, that's the conceptual thing we generated, then what we want to do with multi-evaluate is to say, which aspect of that giant multi-way graph do you actually want to see? That makes sense? Right, so in the usual case of evaluate, we know what we want to see is the fixed point. In the case of multi-evaluate, that's, there are many fixed points. That's probably not what we want to see, et cetera, et cetera, et cetera. Right? I mean, does this make sense to people? People understanding this, not understanding?
I understand.
Picking on somebody, picking on Christopher. Do you believe in this?
Somewhat. I don't know. I mean,
okay.
I have a question about it. So by multi-evaluate, you mean if there is a pattern ambiguity
to all of them.
Yeah, yes. You don't mean the right-hand side of a rule has random real.
No.
Okay.
I mean, in this case, what I'm imagining is yeah, I mean, multi-evaluate as currently imagined, like in the physics project, is a discrete set of possibilities.
Okay, I meant then random integer on the right-hand side.
It has an enumerable set of rules. That's the idea. If you said random choice 7 things, then yes, you could get something like that.
Okay.
Okay, for now we're dealing with, this is an enumerable, a finite set of possibilities at every step.
And they are pre-given, they are not generated dynamically at runtime.
I think they can be generated.
Yeah, I think they can be too. I think that it's the same thing. I mean, they're as pre-given as the code that you normally are running in the usual evaluator. In principle, the evaluator could generate its own tail, so to speak, by generating new code that will then be part of the evaluation process. That isn't the typical thing one does, but one could do it.
Okay.
Right. So what we're saying is finite set of possibilities at every step. And I mean, it really is very much similar to nest graph, for example. In a sense, nest graph and the nest while graph that Brad Klee has been working on, that's now a WFR. Those are types of things that generates. This is this is sort of a generates everything. Well, not quite everything, but that's whereas something where there is a selector. Okay, this is the real question. Again, we've talked about this many times about returning a computation object, and this is really what we need to focus on for making progress on this. We need to get a bunch of these things implemented, a bunch of these, we need to get this thing, again, we've been through it. We need to get evaluation graph implemented. We need to get these pattern, pattern operation things implemented. We need to get multi-evaluate implemented, and a special case. Okay, so remember, what does multi-evaluate return? Evaluate just returns the answer. Multi-evaluate is very unlikely to be able to do that. I mean, there's some cases where we've been through this before, right? What does multi-evaluate return? Okay, so one possibility is a particular fixed point or other single expression. That's one possibility. It could return a.
With what input? Like,
I'm sorry?
With what input? If you just.
Oh, you give it a bunch of rules. Okay, so what does I'm saying, multi-evaluate, I don't know what it is, multi-evaluate of, I don't know which way around it is, probably rules, comma, init. What does it return?
I think this should be lazy because it shouldn't return anything.
Okay, I don't care yeah, fine. This particular thing could return a multi-evaluation, so to speak, could be lazy. Okay, but there's, okay, what can you get from multi-evaluation? That's really the question, right? So you can get a particular fixed point or other single expression with a criterion. Does that make sense to people?
Yeah.
E.g., the smallest number, or e.g., true. Okay, so now, if there's a criterion, so this would be something like, oops. What is that? Is that screen detritus? No. Oh my gosh. It's actually a physical thing on my computer. Never mind. That's funny. I thought it was screen detritus left between those cells, but it's actually a physical spot on my screen. Okay. So, it will be something like find matching result or something. Find or select multi-evaluate. What would it be called? It's the selector. It's the thing that gives you. Okay.
Maybe it should be. It should work similar to scan things like depth first scan, breadth first scan, when you have a bunch of event handlers.
Oh, that's horrifying. Those things are unusable.
But I think it's the same kind of problem. If
It
you
is
can
the same problem. It is the same problem, but we're trying to. Those things are really bad, so we don't want to emulate them. We want to figure out a better way to do it. But I agree that that's worth looking at. I mean, why does down arrow not work here? Why does down arrow not work? Another thing to report. From that position, down arrow.
Sorry, I still have a general question. Can I see a very concrete example of the argument structures? So you have rules. So I couldn't write f of x colon equal x squared, comma, f of x colon equal x cubed, or this is allowed as rules?
No, I was thinking of colon greater than rules for now.
Okay.
Okay. The question of assignments. Okay. Relationship to assignments is a separate issue. Okay. For now, consider disembodied collections of rules, not assignments. not permanent assignments, but we could consider assignments later. Make sense?
Yep. Just wanted to know what.
Yeah, right. So I mean, one thing we could do. What is going on here? There's something really slowing everything down. Yeah, I mean, this is unusable, utterly unusable. How many times have you used it, Nick?
Not many, but I know it is used throughout the like implementation of other stuff.
Some graph theory things use it.
Yeah, right.
Right. So,
I think I've used it like twice.
okay. How mysterious was it to use?
I mean, I had to look it up in great detail every time.
Yeah. So just to be clear here, okay, you've got the multi-evaluation object out. So now I want to extract from it, and it's lazy, but I want to extract from it the smallest value. You know, I've got to think of it as a multi-way graph. See, I mean, okay. Basically, it's extract from the multi-way graph a value according to certain criteria. So, for example, it could be the case that you'll never get the value. It'll take 1,000 steps and you won't know if you're going to get the value. So this extractor has to be able to figure out how far should it go, right? You know, in other words, e.g., you know, get me the simplest expression. Let's say the multi-way graph is doing simplification. Simplest expression that you can get in a reasonable time. Does that make sense? I mean, in other words, there may be many, many expressions that you get out. 10,000, 100,000, 1,000,000 expressions you're getting out. And after a certain number of steps, you want the smallest one, for example. Or you may want to say, you know, another question is, or another one is, you know, we could say another thing would be, does a particular value ever occur in the multi-way graph? That's like a theorem proving thing, right?
But with a time cutoff?
Well, that's the whole point. We're not defining that yet, right? That's the dirty underbelly of the whole thing.
Yeah, right.
Right? I mean, the big issue, the big thing with our ordinary evaluator is we don't give that. 99.39% of the time, you don't use time constraint. It just works. Right?
Yeah.
So this
or
will
you press abort.
Yeah, or you press abort.
Yeah.
The only difference is
or
that
it doesn't work. Yeah.
Right. The main difference is just that in the, you know, most programs you write are not exponential time in the same way that basically every program you write with multi-way or with multi or whatever will be exponential time.
Or could be exponential time. I mean, right. This is what killed Prolog, is that basically, you know, so many of the things you naturally wrote were exponential time. But the thing that I don't know, and I'm now suspicious about, is that by using theorem proving techniques and other things, yes, in principle, it's exponential time. But the question is, what is it in practice?
Well, in practice, a lot of theorem proving stuff is exponential time. So
I know.
Of that, but
I know. So, I mean, it could be, I mean, you know, in general, I think what may be the case is that it's mushy, right? Like, does a particular value ever occur? We may not be able to answer that. That's undecidability for you. Right? So, but the question is, how do we make a function that is useful in the face of undecidability? Because it could also be, I mean, you know, as usual, the answer could be yes, no, or I don't know. right? So the possible answers, yes, no, or unknown.
Which is basically not, it couldn't be found within this time constraint.
Right.
For
And it
instance.
could be that what should be returned in the unknown case is, unknown, where it's some data, and then it is the multi-evaluation object, so that you can always go on and say, well, try harder.
That's a good
You know what
idea.
I'm saying?
That's a good idea. Yeah.
So worst case is you return something, but it's always possible to go further. Now, I mean, I think, okay, so another question that you could ask here is, what is the probability distribution of values of some feature of values? Okay, so that's analogous to learned distribution, right? Where learned distribution is returning a distribution from which you can then do things, right? So for example, let's imagine that we have some agent-based model type thing that's represented by, this can happen, the fox can eat the rabbit can make a burrow, all these kinds of things. Okay, give me the probability distribution of numbers of foxes as a function of time. Is that, Christopher, do you think that's a reasonable, in other words, you would naturally write that code in terms of a bunch of rules.
I guess.
And we've talked about, and the natural representation of what's happening there would be the representation that nobody would do for real or seriously is to make the multivariate graph of every possible fox eating, rabbit burrowing type action. Instead, people would do some kind of Monte Carlo solution, which might be what this does inside.
But in this case, would the probability distribution basically be determined by the path density that leads to each particular outcome, for instance?
Presumably, yes. Although
okay.
one could imagine something where, you see, and this is where things get complicated again, where in the case of, in the usual case of, first choice is the one that's taken, we don't have to define probabilities or any other tagging for the different paths that might be taken by the evaluator.
Sure, because you've elided everything else. Yeah.
Well, yeah, right. But so the first one is the winner, right? But in this case, you might need to tag with probabilities and other such things. But
so everything boils down to traversal, right? We just have to come up with a nice traversal of those multi-way systems and how you would extract properties while we're traversing, and also maintain its state in order to continue it if you want. So it's just to design.
Maintain retain the result of the traversal. That is, if you've got a bunch of walkers walking on the multi-way graph, and then the walkers all give up, you would like to be able to keep going with the walkers continuing to walk as they were walking before. Is that what you mean?
Yeah, some kind of state, like you had this in a known example. You abort your evaluation because you're tired of waiting, but you still have an opportunity to continue it. There should be some kind of state.
Right.
So it's all about like designing this scan function and apply it to the multi-way system that is lazy and not a complete graph.
Yes, right. Now, this relates again to active classification, which is also trying to do things like this. See, I think we've okay. Again, find replace path, which is this function that I really want us to build. We still haven't built it. Is that true?
Only the equational path, which is pretty close.
Okay. Well, we should really build it, because I think it's a very well-defined function that I think is going to be useful. Didn't we had find replace path and we had another function like it, correct?
find the equational path. It just uses the equations. So all your rules are bidirectional. It's like if you only had a way to constrain Waldmeister to use equations only in one direction, I think we can simply have find replace path.
Okay, but find equational path. Michael, can you comment on its utility for expression simplification?
What exactly would it do? I
Given
have
a
two
set of-
equations. And
No,
then,
given a set of equations,
okay.
it will tell you that sine 2x is equal to 2 sine x cos x or whatever, because it can see that there are sub-transformations, that there are 7 sub-transformations that get from one to the other. See what I'm saying?
No, sorry, I don't.
Well, I mean, so for instance, let's take an example.
We already have simplify that uses Waldmeister, right? All the assumptions that you give it. It just constructs all the completions and then applies it to a rule and to construct a normal form to make a simplified version of it.
Look, here's an example. Given this relation, Michael, here, right?
Yeah.
Then we're saying this is an example of that will be a find replace path that gets from this thing here to this thing here. See what I'm saying?
Yes.
That's it.
Okay, so that's much more at a pattern language, not at the level of what you just said of give you a special function identity.
Well, why is a special function identity not a pattern language?
Where do these patterns come from that we apply?
No, we've got a bunch of special function relations.
Yes.
Okay, you know, the multiplication, the duplication formula for the polylogarithm function or something. Okay, and it's a two-way relation.
Yeah.
Okay, so then the question is, can we get from, is it the case that, you know, gamma of x times gamma of 1 minus x equals whatever it is, pi times whatever, right? But we have sub pieces of that relation, right? But we have to go through this giant network to find out whether this is equal to that. That's what this is answering.
I see. I mean, right now, like, there are many things. You have a complicated expression. You say simplify or full simplify, you get something back. But you know, for some reason, there's an easier version. And in virtually all cases, you can test that the complicated one minus the simple one is 0. But in most cases, you can't find the simple one.
I know, but this is about given a set of transformations, can you get to the simple one? Can you get from A to B with these transformations?
Yeah, I see.
Prove the equivalence. I mean, it's basically a theorem proving thing. Now, you know, I have to say, back even in the time of SMP, I was, you know, very keen on this, you know, define a bunch of mathematical replacement rules. But I never really had a good way of using them. And so, like all the, you know, the infinite number of Oleg type rules.
Yeah.
Presumably, in principle, one could throw them all into find equational path and be able to prove things with them. Is that right? I mean, how well does this scale? Nick, if we had 10,000 relations here, would it grind to a horrible halt or would it have a chance?
I think, well, Waldmeister is very efficient, so I'm not sure. I think it's possible.
Okay. Because, I mean, that would be interesting if we could actually do, you know, so, I mean, that's a possible use case is, you know, mathematical expression equivalence via mathematical relations. I mean, that's a long time holy grail. Now, of course, the thing that we're not doing there is extract according to certain criteria, like use the analog of find equational path to simplify things. That's a different thing. That's saying you're flapping around to all these different paths, find the one that leads to the simplest expression. Am I making sense?
Well, we kind of have it. It's like a separate mode. When you search for completion, they're by definition ordered, right? So every rule rewrites into a simple form, into a more simple one. So if you apply all the possible completions, you simplify your expression this way.
Well, I know, but you might have to get more complicated before you get simpler. But my point is here that we need a function that says, you know, I designed all this stuff, so we need to find the design and not, you know, and actually follow it, right? We designed something which was the analog of find replace path that whose goal is to, with respect to a set of transformations, find something that best satisfies a given criterion. That makes sense? Again, there's two general classes of things. Things where you get the answer and things where you get some of the story of how you got to the answer. In our existing evaluator, we are not keeping the story of how you got to the answer, except through things like trace. In this case, we believe it is more necessary to keep how you got to the answer. Does that make sense?
Yeah, we can use proof objects as the state maintaining thing. It's like we have to make them compositional. It's like apply a proof object to another proof object. It's like applying, combining two.
That's a good idea. That's a good idea, and that doesn't work right now.
Yeah.
I don't think it's going to be a proof object exactly, but it is something like a proof object. That's a good idea. We should think through how to make that work. Okay, I'm going to raise one more thing, and then we should probably wrap up for today. But the one more thing is, when the thing goes into an infinite loop, okay, and we've talked about this a little bit before. In the case of the multi-evaluator, even in the case of the ordinary evaluator, this is something we talked about before. In the case of the ordinary evaluator, x equals x plus 1 goes into a loop. Representing that loop is similar to representing this multi-evaluation object, I claim. What is the calculus of these infinite computation objects? I think we talked about this a little bit before. I assume that the best hope for this is the theory of transfinite numbers. But what do we think about this? Is that hopeful? Is it hopeless? What's the story?
What does that mean? Does that mean the loop basically becomes some lazy object?
Yeah, but the issue is, okay, so look, I mean, this is the infinite computations.
Yes.
Right? So this is, you know, the x equals x plus 1 of this world, right? Is you know, aka, let's write it in a replace repeated, you know, of 7 x blank goes to x plus 1. Okay, that's an example of an infinite computation. The question that I have is, okay, if you have an infinite computation, e.g., does x ever get value 111? Okay, that's like asking this question: does a particular value occur in a multi-way graph? Right? This object that we get out should be queryable for things like that. The infinite computation object should be queryable.
Or should it do something smart to just naively?
It should do something smart. It can't do it. There's no way. It has no chance if it isn't trying to do something smart. It has no chance. It'll just going to get, you know, it's just going to flap. It's going to, you know, follow like the Pied Piper. It's going to follow Kurt Gödel into the, you know, into.
Okay, but you mean in this case just going from 7 all the way to 111? Because it could be some astronomical value, and then that's not going to work. That's the point, right?
For example, does x ever get to value? Let me change the question.
Yeah.
Does x ever get to value minus 6?
Right.
Okay.
Yeah,
and the answer is no,
no.
But to prove that is non-trivial.
So we have to have some axiomatic theory of this kind of computation.
Possibly so. Possibly so. I mean, if that's okay. So the next question is there a completeness issue? Right. What is the status of a statement like, does x ever get to value -6? You know, in other words, do we have to? It feels like we have to have an axiomatic system, but do we already have an implicit axiomatic system that is defined by the universal computer plus its set of? In other words, do we need more? Okay, here's the question: do we need axioms beyond what is defined by the definition of the language to answer that question?
Just so I understand, in this case, the point is this entire loop, we know that the values are going to be greater than or equal to 7, right? And so there should be some straightforward way to say, okay, doesn't matter. You don't have to run the whole loop. We know that it's greater than or equal to 7. This is not greater than or equal to 7, so it's not in that loop. Something like that.
Yeah.
Yeah.
Yeah, it's a proof. But I don't know what assumptions. I mean, in the end, my guess is that when it's thrown into, I mean, you know, that one actually does have to decide what one's axiomatic basis is, potentially. But I also, yeah, I mean, there's also the question of composing computations, right? Like, let's say I have, you know, composing infinite computations. Okay, so I've got this infinite computation. I compose another one that subtracts 1. Okay, e.g., you know, so let's do it. We say replace repeated of 7x blank goes to x plus 1, and I want to compose that with replace repeated x blank goes to x minus 1. Okay, now answer the question, can I get the value -6?
What is exactly the meaning of compose?
What I've done there. I take the result from the first thing and I...
But the first one is a repeated one, not a one time. I don't know how many times to repeat.
Exactly.
So shouldn't there not be the x minus 1 somewhere in the third argument of the first one?
No, but I'm saying, here's the point, Michael. This is omega, transfinite number, plus omega, in a sense. Right? In other words, I finish the first replace repeated, which I can't actually do because it's infinite.
I see. So you really want to finish it?
Yes. You finish it and then you apply the second one, which is also infinite.
Okay.
Yeah.
So this is the direct analog of omega plus omega.
Yeah.
Type.
Yeah.
Okay, so the speculation is that there is a way to, you know, that just as we can talk symbolically about infinite numbers in transfinite, in the theory of transfinite numbers, so we can talk about infinite computations in a similarly symbolic way. And the whole point is that in this multi-evaluation thing, that I claim it will become much more routine for there to be non-terminating computations. Now, maybe I'm wrong about that. You know, you might have thought that in the normal course of Wolfram language affairs, you would get lots of non-terminating computations, but we don't.
I think we do, but we know how to deal with them, like an infinite sum.
Okay, that's interesting. Okay, so there's an interesting question. Convergence for infinite computations. CF infinite sums. Okay, so here's a question, Michael. Given, this is a very interesting question. Does convergence require the continuum?
I think yes.
So the
James surely knows the answer to this one, I guess.
James or Xerxes or anybody here who has a
I mean, Munich.
Look,
Well, so it must depend on the nature of the convergence, right?
Yeah. I mean, normal one that we normally use the word for.
Well, the epsilon delta type story is going to depend on the continuum.
Yeah.
Yes.
But the question is there any sense? You see, there is a convergence. If you have a property, I can imagine a situation in which the property, in which even though the actual data structure is, getting bigger or whatever it's doing, the property is gradually converging.
What's an example?
An example would be
sum of 2 to the minus k. The thing gets bigger and bigger and bigger, but the result is very simple.
Well, I was thinking of a different kind of thing. I was thinking of the multi-way system that says x blank, let's see, list, x double blank, triple blank. Okay, let's try this. Goes to xa, multi-way system like this. This is really funky. Okay. Goes to xb. Okay. The question now is, are there an equal number of a's and b's in the list? The answer is that converges. The fraction of a's in the list converges to a half, I think. Even though the computation is infinite, the list is just extruding forever. A property nevertheless converges.
But the property stays small at any time. It never gets big.
I agree. But what is big? I mean,
I think, again, sum of 2 to the minus k from k equals 0 to n becomes arbitrarily big, yet the finite result is simple.
What?
Okay, from k equal 1 to n, for any n, it will get bigger and bigger and bigger.
Am I being stupid here? If I say table of that, n goes up to 10. It just converges to 1, right?
Yes, but that is my point. The convergent one is simple, but the trillionth term is pretty big.
N is big, but the behavior is asymptotic. That's the point.
But,
right,
but the individual terms are getting smaller and smaller.
No,
but representation-wise, they get bigger.
Oh,
not numerical value-wise.
Oh, I see.
Okay.
Their byte count.
Okay.
That's interesting. But the reals, I mean, this is the life of the observer. The reals are an observation. That's actually an interesting example of a case where the observer's version of this is just the numerical value, whereas the underlying structure is this, rational number with a large number of digits.
Right.
All right, I think we are beginning to get, I'm hoping that Nick is going to have a chance to really dig in and work on a bunch of this stuff. I think we have some pretty definite things to go ahead and try and implement. And I think I think we're getting a pretty decent design for this. And I think we can, we know some specific things. We know these things here for functions operating on patterns. We know some stuff here with multi-evaluation. And I predict that we have a big issue about, for example, which, for example, there'll be a common, which branch do we go on? And I suspect there may be some somewhat generic machine learning kinds of things we can do for that go beyond. I don't know whether that's. I mean, that's a place where we can imagine inserting some different technology.
That would be cool. Yeah, that would be cool.
But I mean, the basic point here is to get us to the point where, find, replace path, things like that are routinely usable. And where, for example, the stuff I've just been looking at with, with games and so on is trivially programmable by these methods. And again, where branch yield graphs are extractable, blah, blah, blah. We've talked about this a zillion times. And where the evaluation front, which becomes important for multi-evaluation, is definable. Nick, does this make sense to you?
Yeah. It's just a continuation of the multi-object project.
Yes, it is. Yes, it is. It's just we need to, I think, just define how to bring that into something where we can, have the subsystem that is these things. And I mean, then the stretch goal of that project is to see how it interacts with the compiler and how we can actually get some of these multi things executed across multiple processors and things. Does that seem undoable or impossible, or does anybody have any comment on that?
Well, by me alone, it's impossible.
Well, I understand, but I mean, I'm saying, okay. I think we need to wrap up here. All right. Well, to be continued. I mean, we are converging despite all these, but we just need to focus on, I think I'm now convinced. I think I've got the intuition now, maybe, for what type theory is and what it isn't.
Well, good. I think this was a worthwhile conversation to have.
Yeah, and I think I think it is unsurprising that type theory is what you need to bring a compiler to heel, so to speak. It is also unsurprising that type theory is unmagic in bringing computational irreducibility to heel.
Yeah, right. Exactly.
So, I mean, it's a way of organizing computations that is useful for certain kinds of purposes. And yeah, and it doesn't do anything magic. And I think that's, I mean, again, it may be relevant in this infinite computation story. There may be a way of, what can be brought to heel there.
Yeah, right. It's basically anything that's reducible in the hyperboolean, more or less. The lazy object will just be some sort of type
Yes.
there. Yeah, right. Or yeah.
Well, okay. So the claim is what can be manipulated / represented is something like a type in the hyperroolead. I bet we don't have hyperroolead in the spelling dictionary. Oh, we do. Well, yeah, I mean, and the thing about these infinite computations is, just like Cantor normal form for transfinite numbers, there will be some similar kind of canonicalization or not for these infinite computations. I mean, if we don't have to deal with infinite computations, it's all the better. But I have this feeling that in the case of, in this multi-evaluate thing, that we won't have a choice, that they'll be much more generically showing up than they do in standard evaluation. All right. Time to wrap up here. Thanks, everybody, and to be continued another time. Okay.